Part 4 of Unit 11 is about equilibrium calculations. So here is a relatively straightforward equilibrium problem. A closed system initially containing 1 times 10 to the negative third molar hydrogen gas and 2 times 10 to the negative third molar iodine gas at 448 degrees Celsius is allowed to reach equilibrium. Analysis of the equilibrium mixture shows that the concentration of hydrogen iodide is 1.87 times 10 to the negative third molar. Calculate Kc at 448 degrees Celsius for the reaction taking place, which is given below. So that was a lot to take in, and it probably didn't make a whole lot of sense, but it's okay. We've got a special tool to help us solve these problems, and that tool is called a Rice table. A Rice table has 4 parts, R, I, C, and E, and what it stands for is reaction, initial, change, and equilibrium. Now, the initial, change, and equilibrium, those are all referring to concentrations of products or reactants. So what they initially were, how the concentration changed, and what they were at equilibrium. And the R is a reminder to write the balanced reaction because we know that rates are related by the stoichiometric coefficients in the balanced equation. So let's attack that problem from a couple slides ago. The reaction was hydrogen plus iodide yielded, and we'll use our double equilibrium arrow, to hydrogen iodide. So there's my balanced equation. It looks a little bit ugly on this slide, but you get the general idea. H2 plus I2 yields 2HI. And they told us the initial concentrations of the reactants. For hydrogen, it was 1 times 10 to the negative third. And they've given us the molar up here in the brackets. That means molarity. I'm just going to leave the M out of here. For iodine, it was 2 times 10 to the negative third. Now, the initial concentration of HI, the product, is going to be 0, because initially there was no product. We combined this much of each reactant, and we eventually made the product, but there wasn't any at the beginning. Now, they told us that at equilibrium, there was 1.87 times 10 to the negative third molar hydrogen iodide. That's our product. We now have enough information to fill in the rest of the blanks on this Rice table to eventually solve for K, the equilibrium constant. Because we know that to solve for K, we need the concentrations of all the parts at equilibrium. Well, the product started at 0 and went to 1.87 times 10 to the negative third. So that is a change of plus 1.87 times 10 to the negative third. The reactant concentrations are going to decrease because they're being used up in a reaction. And we have to go back and double check the coefficients at this point. We've got 2 in front of HI and 1s in front of the 2 reactants. That means that this product appears twice as fast as the reactants are used up. So the change for each reactant is going to be half the change for the one product here. So we're going to divide this by 2, and we're going to end up with a change for each reactant of minus 9.35 times 10 to the negative fourth. That's the same for both of them because they have the same coefficient. So to fill out this equilibrium part, we just need to subtract 1 times 10 to the negative third minus 9.35 times 10 to the negative fourth. That's going to give us 6.5 times 10 to the negative fifth at equilibrium for H2, and then 2 times 10 to the negative third minus 9.35 times 10 to the negative fourth is going to give us 1.07 times 10 to the negative third. Now we've solved for the concentration of each part of the reaction at equilibrium. So we're going to take those equilibrium values and plug them into our equilibrium expression to solve for K. Our equilibrium expression, K, is equal to the concentration of the products squared, because it has a coefficient of 2, and the reactants to the first power, but they're going to be multiplied by each other, products over reactants. Now we're going to plug in those equilibrium concentrations from the table before, so it's going to be 1.87 times 10 to the negative third squared, that was the concentration of the product at equilibrium, divided by the reactant equilibrium concentrations. 6.5 times 10 to the negative fifth times 1.07 times 10 to the negative third. And when we do all of our math there, we're going to come up with K being equal to 50.3. And remember, there are no units for the equilibrium constant. So let's look at another problem. At 900 Kelvin, the following reaction has a Kp, that's pressure, of 0.345. And then there's our balanced equation. 2SO2 plus O2 is the equilibrium with 2SO3. In an equilibrium mixture, the partial pressures of SO2 and O2 are 0.165 atmospheres and 0.755 atmospheres respectively. What is the equilibrium pressure of SO3? Well, we're going to use a Rice table to set this up. We're going to use a Rice table for just about every equilibrium problem, so I'm going to plug in the coefficients for my reaction here. And then I had a 2SO3, we're at equilibrium. Now let's plug in the information that we know. This is our product. Initially, there was none of it. They told us that at equilibrium, the pressure of SO2 was 0.165 atmospheres, and for O2 it was 0.755. They also told us what Kp was. Kp was 0.345. So we need to solve for the equilibrium pressure of SO3, and we've got enough information to do it. Looking at the balanced equation, we don't actually know what these initial concentrations of the reactants are, but we don't need to, because we know that this was a plus 2x, and this was a minus 2x, and this was a minus x. That means this has to be plus 2x because of the coefficients of the balanced equation. So at equilibrium, we've got 2x. We don't know exactly what x is. However, we do actually know what the value of k is for this. So we can set up an algebra problem to solve for x using these equilibrium values. So our equilibrium expression, K is equal to the pressure of SO3 squared divided by the pressure of the SO2 squared times the pressure of the O2. Those are all equilibrium pressures. So we'll plug in the information we have from the Rice table. We know what K is. It's 0.345. We're not sure what the equilibrium pressure of the product is. We're going to go ahead and plug in that 2x squared up here. The pressure of the SO2 was 0.165, and it's squared, times the pressure of the O2, which is 0.755. So we need to solve this for x. So what we'll do is square this, multiply it by 0.755, and then multiply it by 0.345. When we do that, we get 0.00709 is equal to, we'll go ahead and simplify this too. We're going to have 2x squared becomes 4x squared. So we'll divide this by 4 and then take the square root of it. So we end up with x being equal to 0.042 atmospheres. Now, that is not our final answer because the equilibrium pressure of SO3 was 2x. So we're going to multiply this by 2. So our equilibrium pressure of SO3 is 0.084 atmospheres. If it was just 1x, we would have left it at 0.042. But since in our equilibrium box we had 2x, we had to multiply it by 2. Okay, your question for this section. What is the missing value in the following rice table? So basically, what is x in this rice table?